Okay, so now let's transition we're still part of lesson 2. We're still talking about heat and how we calculate it. But instead of calculating the whole heat of like a specific chemical reaction, we're going to look at specific chemicals or materials, metals, that sort of thing. So first, let's have just kind of a thought experiment. Okay, let's think, which container holds the most heat if they're both at 30 degrees, a coffee cup or a bathtub? So what I want you to do is I want you to think, okay, if you have a bathtub, a square is not a bathtub, let's say, I don't know, bathtub, it's got a little shower, okay, it's got water coming out. Obviously, this is the most beautiful drawing ever, and it's filled with a whole bunch of water. Okay, and then you have like a little coffee cup that's also got some water in it, okay, which I didn't color inside the lines there, so there we go. Okay, it's got a coffee cup. They're both at 30 degrees Celsius, so the water in the tub is at 30 degrees, and this wasn't at 30 degrees. Which one holds the most heat? So which one actually has the most heat in it? Okay, so what I want you to do is just pause the video and like write down your prediction. What do you actually think? So go ahead and pause, press play when you've got your prediction written down. Okay, so some of you might have said, well, they're both at 30 degrees, so they have the same amount of heat. But we know that the bathtub has a lot of water in the bathtub, right? And so because it has more water, even though it's at the same temperature, we know that it is faster to heat up a small amount of water, like in a coffee cup versus a shower. So the bathtub will have more heat energy in it because of the larger mass. Because it has a larger mass in grams of water, it will have more heat energy because you have to put a lot more in to get it at 30 degrees. And so this concept of how different substances will require more heat for a certain temperature, it's kind of all related to this concept called specific heat capacity, which is represented by a capital letter C. Key thing to note is that this is a capital letter, not a lowercase letter, because a lowercase letter c means something different. A capital letter C, or our heat capacity, is the amount of heat it takes to raise the temperature of, I think there's an extra blank. Raise the temperature of, sorry. 1 gram of the substance by 1 degree Celsius. So if you just have like 1 gram, so like a small amount of whatever your substance is, and you want to increase its temperature by 1 degree Celsius, it requires a certain amount of heat or energy. So this is often just abbreviated and shortened as just specific heat instead of specific heat capacity. And when we look at water, water has a huge value compared to other chemicals. So for water, the specific heat capacity is 4.184 joules per grams degrees Celsius, which those units are already there in your notes. And so this means for water, it takes 4 joules of energy to increase the temperature. So for example, most metals, so like specific heat of a metal is typically around like 0.26 joules per grams degrees Celsius. Like you'll have it in a range there. So you can see that if you compare that to water, for example, which is 4.184, that's a difference in magnitude of about 1,000. This is why like metal seat buckles in your car are gonna burn your hand, but you've left water in your car at the exact same time, and even though it's warm, it's not, burning your skin off like a seat buckle can in the summertime. So for water, what this implies is that it takes a long time to heat up But that also means it takes a long time to cool down as well. But this is why, in a pool, you might have a pool full of water during the summertime, but it feels great. But the concrete or the wood around the pool is about to burn your feet, or the sand at the beach. And so the formula we use for this is Q equals MC delta T. And so this triangle is the Greek, it's the Greek letter delta, which you might be familiar with from fraternities and sororities. So we're going to go through what each of these variables mean, okay? So Q is your heat energy, which I know is annoying, that's not an H, and its unit is joules. So the unit right here is joules, okay? M is our mass, as usual, and our unit is grams. Again, we've been working with mass and grams since August, so you should be familiar with this. Delta T means change in temperature. So the delta is the change in, and it's measured in degrees Celsius. So this is our unit. We do not use Fahrenheit in science. Okay, and so one way to find the change in temperature is that it's your final temperature minus your initial temperature. Okay, and so one thing to note is anytime you're in science or something like that, if you have something like this, where you have T final, typically the big letter or the thing that's not like a subscript is your variable, and then this one is like an identifier, like it tells you which one you're referring to. So for example here, both of these have a specific heat capacity variable, but then the subscript tells you which specific heat you're talking about, whether it's of a metal or water or things like that. And so this is our formula. The formula is on your periodic table. So you do not have to memorize it, but you have to remember when you need to use it. Okay, so remembering what each of the letters mean, what their units are, and how to figure out a problem that you need to use. So let's look at that example. So for example, if we think back to the bathtub and the coffee cup, if we actually put exact numbers to it, we can actually calculate what we have. So if a bathtub contains 500 grams of water and a coffee cup contains 50 grams of water at 30 degrees Celsius, which container has the most heat energy? The specific heat of water is 4.184 joules per grams degrees Celsius. So what we're going to do is they want to know which container has the most heat energy. So they're saying, what is Q equal to? So we're going to set this up into two different categories because we're comparing two things, right? We're comparing the bathtub to the coffee cup. So we need to make a list of all of our givens. What are the things that we have? So one thing we know is that we have a mass of water. So I'm going to put M of H2O is 500 grams, but that the mass of the cup, the coffee cup, is 50 grams. And we know that the specific heat of water is 4.184 joules per grams degrees Celsius. And even though they say it's at 30 degrees, we're just going to assume that our change in temperature for both objects is 30 degrees Celsius, and Q is what we're looking for. Okay, so what we do first is, we write down our formula. So Q is equal to our mass times our specific heat times our change in temperature. So what we'll do first is we'll solve Q for the bathtub. Okay. So actually here I should have put the tub for our original mass. So that would be the mass of the tub times the specific heat of the water times the change in temperature. So the mass of our tub is 500 grams of water times 4.184 joules per grams degrees Celsius times our change in temperature, which is 30 degrees Celsius. So notice I'm putting these all in parentheses to keep my units and numbers from getting jumbled up. And then when they're touching like this, that means we will multiply. So when we look at our units, we see that grams per degree Celsius is in the denominator of our fraction here. And so what happens is we have grams cancel out with grams, degrees Celsius cancels out with degrees Celsius. Joules is our only remaining unit. So that means Q of our tub is equal, we'll have units of joules, which is good because Q is measured in joules. And then we take our numbers and we just multiply them all together. So 500 times 4.184 times 30 is going to give us 62,760 joules. So that's quite a bit. And so we can now compare this to the cup. So Q of the cup is the same thing, but instead of the mass of our tub, we have the mass of our cup, which is 50 grams, times 4.184 joules per grams degrees Celsius, times 30 degrees Celsius. So most of this was the same. So grams cancel out with grams, Celsius with Celsius. But we know for a fact that there is less mass, there's less water in the cup. So 50 times 4.184 times 30 gives you 6,276. So very, very similar. And what we can say is, which container has the most heat energy? We can say the tub has the most, which I spelled that wrong. The tub has the most heat energy. Okay, this is our answer based on the calculation and not just our assumption. So one of the next examples we have, example number 2 says if 297 joules of energy are used to change a block of aluminum from 22 degrees Celsius to 55 degrees Celsius, what was the mass in grams of the aluminum block? Okay, so again, we write down kind of what we're given. So remember the guess method, given, unknown, equation, substitute, and solve. So we write down our given. We see this number here, 297 joules. Because that says a J for joules, we know this is Q. So Q is 297 joules. We see some temperatures here. It says it changes from 22 to 55, so that means our initial temperature, so TI, is 22 degrees Celsius, and our final temperature, or TF, is 55 degrees Celsius. They tell us that the specific heat of aluminum is 0.90 joules per grams degrees Celsius. Okay, so these are all the things we know. And the question really says, what was the mass in grams? So the mass of the aluminum is what we are looking for to try to find. So we've got our given, we've got our unknown. We know that our equation is going to be Q times M times C times delta T. And one thing to note is we know that Q equals M times C, and that delta T is our final temperature minus our initial temperature. And so we can calculate that first. So we want to substitute our stuff in. So we've got 297 joules for our Q. We do not know what the mass is. We know that our specific heat of aluminum is 0.90 joules per grams degrees Celsius. And then our final temperature was 55 degrees Celsius minus a 22 degrees Celsius. So what we can do is we can simplify. We know that 55 minus 22 is going to give us 33 degrees Celsius if we simplify that. If we simplify the right side further by multiplying the 33 degrees times the 0.90, we get that the right side is M times 29.7 joules per gram. So notice that the Celsius is going to cancel out with the Celsius here. Okay, so we get joules per gram times M equals 297 joules. And so to get M all by itself, we do the opposite of the math. So we divide by 29.7 joules per gram on both sides. So see, this cancels out, and that M is equal to, let's see, joules cancel out. So 297 divided by 29.7 gives us 10 grams, because the G is all that's left, which is good because mass is measured in grams, so that's just fine. We know that the mass of our aluminum block was 10 grams. And so what you should see is some practice problems for both the first part of the lesson with Hess's Law on the previous video and some practice problems. Your answers are in red at the end because remember, the whole goal is to build your confidence. Can you do these problems and get them correct? So notice you're given 8 practice problems altogether, which means you should really be able to demonstrate your understanding by the end. There is a ticket out the door, so please make sure that you really pay attention.